All right, so let's get started. Let me remind you. So today we're talking about the residue calculus. So we'll be mostly focused today on how to calculate residues, and I'll share with you a few useful tips and tricks. But to start with, let me just give you the definition, yeah? So definition, f of z, if f of z has isolated singularity at z naught, all right? And Laurent series f of z equals to the sum n equals minus infinity to infinity of a sub n z minus z naught to the power n, all right, for, let's say, 0 less than modulus of z minus z naught less than rho, all right, then we define res bracket f of z comma z naught, all right, equal to a sub minus 1. What's the significance of this? Who cares, right? Well, if we have a picture, right, and we picture, say, z naught here, right, and then, you know, maybe rho, and the rho doesn't have to be finite, right? Rho could be infinity, okay? But I'll picture rho finite here just for the sake of discussion, yeah? Okay? So if you have any, you know, closed path around here, counterclockwise oriented, right? Then what's the integral? What's the integral of f of z dz around that path? Let me call it c. Well, that integral you can calculate from the Laurent series, right? So it's equal to the integral over that thing of the sum n equals minus infinity to infinity of a sub n z minus z naught to the power n dz. But the thing is, the convergence of this Laurent series is normal, meaning that it's uniformly convergent on that curve, meaning that we can switch the order of integration and summation. And so, flipping that around, we just get the sum n equals minus infinity to infinity of like a sub n integral of z minus z naught to the power n dz over c, all right? But hey, z minus z naught to the n is what? That's holomorphic, right? Well, I should be careful here. Anyway, the point is there's a deformation theorem, which I haven't, I suppose, technically proved for you guys yet, because there is an argument which I need to give you in a separate video where I need to be careful about that theorem and do it carefully for you. I haven't done that in class yet. My apologies. But I will get around to it. But the point is, you could deform that whatever curve, right, to straight up a circle inside there, right? I could replace that with the counterclockwise oriented circle, say circle of radius r, right? where r is small enough to be inside the red curve, right? And so as long as the point z0 is in the interior of the region defined by the red loop, we can make this deformation, right? And the integral over c will be the same as the integral over CR using the deformation theorem. But then the thing is, we've already calculated that the integral of z minus z0 to the n over a circle is always 0, right? It's always 0. This is the circle centered at z0, of course, right? So this integral right here is 2 pi I Kronecker delta of n comma minus 1. In other words, what I'm saying is it's always 0, except when it's 2 pi I. And when is it 2 pi I? It's only 2 pi I when n is equal to minus 1, only for the case that you have a reciprocal power. This is a calculation we've done. That just comes from putting the explicit parameterization of the circle into the integral and just doing the calculation, right? So maybe I should do that, actually, because I think you guys are a little shaky on that. So here's CR. Z minus Z0 to the power n dz. So how do you calculate this integral? CR has parameterization Z0 plus R e to the I theta, right? This is the parameterization of C sub R. And so what's dz? dz is R I e to the I theta d theta. And so we integrate from 0 to 2 pi. Z minus Z0 to the n is R to the n e to the I theta to the n, yeah? And then we've got R I e to the I theta d theta. So what all that gives us is R to the n plus 1, well, IR to the n plus 1, integral from 0 to 2 pi of e to the n plus 1 I theta d theta. And now there are two cases, right? If n plus 1 is equal to 0, right? So how does this work out? This is either equal to I r to the n plus 1 integral from 0 to 2 pi of d theta, right? If n plus 1 equals to 0. Or it's equal to 0 if n plus 1 is not equal to 0. Why is it equal to 0? What is e to the n plus 1 I theta when n plus 1 is not equal to 0? That's the integral of cosine n plus 1 theta plus I sine n plus 1 theta. But we're integrating sine or cosine, right, of n plus 1 times theta, right, over a 0 to 2 pi interval, right? So that is over a multiple of cycles, okay, because cosine of 0 and cosine of n plus 1 times 2 pi are both 1, and likewise the sine of any integer multiple of pi is 0. So you get 1 minus 1, or you get 0 minus 0 as you calculate that. The point is, if n plus 1 is not 0, this integrates to 0 because it's integrating sine and cosine over a full multiple of cycles. All right? So this can only be non-zero if n plus 1 is equal to 0, which is to say n is equal to minus 1, right? So what's my point? This integral, right, just breaks down to what? So if this is only 0 when n is equal to minus 1, we're just left with actually 2 pi I a to the minus 1. So do you see why we care? Why do we care? Because the integral, right, the integral over our curve, right, of f of z dz, what is it equal to? It's just equal to 2 pi I residue of f of z comma z naught, right? Now what is the where we do what? Where we suppose f of z has just one isolated singularity, right? z naught within the curve. The counterclockwise closed curve C. So this means we can do an integration by just calculating the Laurent series, right? Here's an example. Suppose I'm looking at f of z equal to, 1 over z squared plus 1, right? And we'll look at this, and we're going to integrate over, let me draw a picture of it. Say this circle, right? So this is the circle modulus of z minus I equal to 1. So how would we calculate the integral of dz over z squared plus 1 over that circle, counterclockwise oriented, yeah? So we look at the function, right? F of z equals 1 over z squared plus 1. What are its singular points? I and?
Is it 0?
Yeah.
Is it I minus?
Right, so we need to factor, right? 1 over z squared plus 1 is 1 over what? Z plus I, z minus I. So we have singular points. Z equals to plus or minus I, right? Those are the troublemakers. Now let me draw a picture of those. I like to draw singular points as like little x's. So you've got I, which is at the center of the circle we're integrating, right? And you got minus I down here, right? So the theorem says we only need to care about which one? I, right? The minus I doesn't affect us, basically, is what the theorem's saying. And so this is going to be equal to 2 pi I res of the function, yeah? 1 over z squared plus 1 at what? At I, yeah? And so if we can learn how to calculate the residue of 1 over z squared plus 1 at I, then we can finish this integral, okay? So we'll circle back to this example. I want to share with you some theorems about how to calculate residues, right? So here's the tips and tricks. I believe I have 4 sort of, you might call them cheats almost. They're just quick ways to get the residue from something, okay? So I have examples in the notes I'm skipping over. I'll come back to them, okay? I want to give you the rules first. So here's rule 1. If f of z has a simple pole at z naught, then the residue of f of z at z naught is equal to the limit as z goes to z naught of z minus z naught times f of z. All right? Rule number 2. if f of z has double pole at z naught, then the residue of f of z at z naught is equal to the limit as z goes to z naught of d dz of, you multiply your function by z minus z naught squared f of z. All right. Rule 3. Obviously, I should come back and prove these rules for you, right? I want to get them all on the page so you understand like the rules, and then we'll cycle back to the proofs, okay? Or examples. So if f and g are analytic at z naught, what does that mean? What does it mean for the holomorphic on what? On some open disk centered at z naught, right? There has to exist some, right? And if g has a simple zero, what's that mean? Then the residue of f of z over g of z, all right, at z naught is equal to f of z naught over g prime of z naught. Ooh, I like that one. Look at that, no limit, yeah? I like that one a lot. What does it mean for g to have a simple zero at z naught? Let me remind you of that, yeah? How do we define simple zero at z naught? What does this mean? This means g of z naught is 0, right? And what else? Simple 0 means it's not repeated, right? So the way to test that is to check if the derivative also has a 0. See, if the derivative of g at z naught is not 0, that tells us that it wasn't a double 0, right? Do you see why that is?
Yeah.
I mean, if g of z had a z minus z naught squared in its expansion, when you differentiate that, you get a 2 times z minus z naught, which when you plug in 0, it's still 0. So when you plug in z naught, it's still 0. So this is very nice. I think this is a definite candidate for us calculating the residue in example 1, right? I think this is the one to go with for our example 1. Let me finish the story here. Rule 4. Rule 4 says what? Rule 4 says if g of z has a simple... See, I think that's a typo. If g of z, this is a typo in my notes, has simple, I say pole, but I meant 0 at z naught, all right? Then the residue of 1 over g of z at z naught is equal to 1 over g prime of z naught. Ooh, I think actually rule 4 is the one to go with, isn't it?
Yeah, it's rule 3 and rule 4. Very similar.
Yeah, exactly. So if you prove rule 3, rule 4 is easy to prove, right? Because if rule 3 is true, we just take f equal to 1 in rule 3 and we get rule 4, right? So let's apply rule 4 to calculate the residue here. So identify we've got g of z equal to z squared plus 1 with g of I equal to I squared plus 1, which is minus 1 plus 1, which is 0, right? And g prime of z is what? It's 2z, right? Thus, g prime of I is equal to 2i, which is not equal to 0. Hence what? and z naught equal to I is simple 0, right? As we need. It's a simple 0. So consequently, by rule 4, what do we find? The residue of 1 over z squared plus 1 at I, 1 over g prime of I, right? Which is, apparently, 1 over 2i, right?
Oh, we play at I.
Right. We have to evaluate at I. In this case, I'm letting z not be I. To evaluate at I. And okay, so then we go plug that back up into, by the way, this up here, this is known as the residue theorem. Truth be trolled, listen to me. Truth be trolled, that's what Audrey does. I got a nice. My comedy was acknowledged. What's happening? No way. I was telling my daughter that she has that in common with you. Like, you both are like immune to my jokes. And because I was making good jokes in math yesterday, but she was not acknowledging them. Okay, they weren't really good jokes. They were just stupid puns. But anyway, the residue, this is the residue theorem. But the truth be told, this is a special case of the residue theorem. The full-blown residue theorem I will share with you shortly, okay? But when we just have one residue inside the curve, this is the residue theorem. And so what we just found is that this is 2 pi I divided by apparently 2i, right? So what's the answer here? Pi. This integral is pi. That's really nice. It didn't even require anti-differentiation. We really just integrated by differentiation here, if you look at it, the calculus of it. That's really weird. All right. So what's the full residue theorem? Okay? So suppose you have a curve, all right? And suppose that you don't have one isolated singularity. Suppose you got a bunch of them, all right? Suppose you got a bunch of isolated singularities. Yeah, finitely many. Yeah, I'm not. They don't pay me enough to do infinitely many. Sorry. Maybe once I get PhD students or something and a reduction in hours I teach, maybe we could do that. But sorry, for the moment, no. Sorry, let me stop being an idiot. That's not likely to happen. But hey, let's call the residues Z1, I'll do little x's, Z1, Z2, Z3, et cetera, right? Z4, let's say there's m of them, all right? And suppose you've got a curve, all right? That encircles all of them, yeah? In the counterclockwise sense. C. See, what you can do then is you can take that curve and you can sort of make some, this is going to look like one of those, ever been to the butcher and see one of those like things where they segment the meat into the different, kinds of cuts of meats that you have. Ever seen one of those pictures at like the grocery store or whatever? It's kind of like that, right? You can draw like little regions and put in these sort of cross cuts, right? So like this one, I can go this way on one side, I can go this way on the other side, right? This one here, I can go this way up here, but I can go this way down here. I gotta be careful here. So, like here, like that. Maybe I should avoid doing that kind of cut. That's confusing me. Oh no, it's fine. So this way down here, this way here. So what I'm trying to say is all of these dotted lines, I'm not just adjoining one of the curves, I'm adjoining a pair of curves which are oppositely oriented, which means what? I'm really adding 0 to the integral, right? Because if you add both, the same point set, but the same point set, right? But going one way and then the other way. So you're really adjoining two curves that are oppositely oriented. The integral says the integral of a curve is equal to minus the integral over the reverse of the curve, right? So we're just adding 0 to the integral. And the curves don't cut through any of the singularities, right? And so then basically we can say the integral of f of z dz. And so I'm supposing that f of z has isolated singularities z1, z2, zm. Come on. This board moves so much within C, right? So then this is going to be equal to the sum let's say j equals 1 to m of the integral over, let's call it cj of f of z dz. So let me show you what I mean by C1. C1c is just this basically this curve here, okay? See it?
It's the same song and dance as the crosscut here.
It is exactly the crosscut idea. This is a similar argument needed to be made before. I don't think I ever quite did it in class. And then C2 would be like this run here, right? So now I'm drawing these curves as if they're separate because, well, I have to because of the picture to communicate the idea, but really I want these to be the same literal, they're actually the same, on the same line here, and the red and the green, okay? That's my initial move. And then my next move is, okay, well then by the deformation theorem, see, because the f of z is holomorphic, right, inside the green curve, right up to the singularity, well, I can shrink these, I can shrink these as appropriate to circles on which what? Which kind of circles do I want to shrink it to? I want to shrink it to the circles on which there exists a Laurent series expansion about that singular point. All right, so make the circle small enough so that there exists a Laurent series expansion for the function about that circle. And I'm going to call this shrunk circle C tilde.
Do we have that? There always exists a Laurent series around the singularity?
Yes, that was the start of chapter 6, is that there exists a Laurent decomposition for a function that's holomorphic on an annulus. And these are punctured, this is like a punctured curve, which is it
unique or is it just?
Yeah, so I guess I need to extend the annulus result to like a punctured closed curve, but the deformation theorem basically does that. So then the point is, I can write that as as what? This is, so then then I apply the residue theorem that I worked out at the start of class on each C sub j tilde, right? Does that make sense? So I just apply the thing I worked out at the start of class that I've erased at this point on each one of those. And here, I'll draw the picture in here. If I have a different color, I don't know. So see, I'm thinking of the C sub 1 tilde as like a little circle like this. And here's there's like a little C sub 3 tilde like that, etc., on which I can find the Laurent expansion. And then I can apply the residue theorem at each pole, and that gives me what? The sum j equals 1 to m of 2 pi I res f of z at z sub j. So in other words, I just have to add up 2 pi I times each residue that's within the curve, and that gives me the integral. That is weird, isn't it? Yeah. And that's the full residue theorem, okay?
Is there a particular problem they were trying to solve?
You can also extend this to infinity, right? You can look at the residue at infinity and look at an exterior, like an exterior region. So if you have an isolated singularity at infinity, you can do the integral. You could do like an integral. So to think about it in terms of the complex plane, if infinity is your singularity, right? Then how do you? What's a counterclockwise oriented? I think let's see, if I want out here to be inside my region, right?
You go the opposite way.
I need to think about how do I walk around this so that it's on my left. I think I have to go clockwise in that case. I want to say, if I think about going clockwise, the outside's on my left, right?
Yeah.
So I believe that I need to check on this. Actually, I'm pretty sure this is true, but I honestly I'm not sure I've ever taught this, so it gives me a moment's pause. But I think this is actually true. If my brother's right.
So would you make it?
Now, I'm not confident this would be true if you had an essential singularity at infinity. That just it worries me for some reason. But anyway, let me back up a bit here. Conjecture, yeah. Okay, conjecture. I'm gonna hedge my bets here a bit. All right, so I'll let you guys choose your adventure today. Would you rather me prove rules 1 and 2 and 3, or do more examples of residues?
Are these the only rules we have?
Yes, I should mention these rules are actually from Churchill's Complex Analysis, which is a book many people in my generation learned from. Churchill's Complex. I think it's Complex Variables book. It's got like, I don't know how many editions. This is the book I learned out of, which is, it's a good book in its way, but it's also very poor in other ways. So.
It's just calculus, right? Okay. Since all we have are these rules, is there any other way to calculate the residue that we should know about? Or is it just
Other ways to calculate the residue, the geometric series, like sometimes let's just look at some examples. All right, so I'll prove these rules later. Is that the consensus? Yeah. Okay. Oh, fine, I'll prove them now. So simple, what does it mean f of z has a simple pole at z naught?
as one singular point inside the curve?
Right, it means that f of z is equal to the sum, right? N equals -1 to infinity of a sub n z minus z naught, right, to the power n. And so what happens if you take, z minus z naught times f of z. So let's just try to calculate the limit directly. So we're calculating with this, right? Which is the limit. C goes to z naught to sum. And what we got? We got z minus z naught to the what? N plus 1, right? So if n is what? N is greater than or equal to minus 1, which means n plus 1 is what? Greater than or equal to 0. Agree?
Yes.
So what can you tell me about, and then again, using the uniform convergence, we can flip the limit in the summation. Yeah? Pull the constant out. Take the limit. How does this limit work? So just think about that limit. If n is greater than, or if n plus 1 is greater than 0, that limit is clearly 0, right? Because the limit of z minus z naught is 0 as z approaches z naught. And so is any power of z minus z naught, right? So the only way this can be, so this is what? This is either equal to, so basically this works out to Kronecker delta of 0 comma n plus 1, right? And the reason I say that because if n plus 1 is equal to 0, what is that? That's just the 1. It's a constant function, right? If n plus 1, so it's either 0 if n plus 1 is greater than 0, or it's 1 if n plus 1 equals to 0. See, because n plus 1 equal to 0 makes this just the constant function 1, which limits to 1. And so, long story short, this is just a minus 1. Because the only way that can be non-zero in that sum is when n plus 1 is equal to 0, which is to say n is equal to minus 1, and then you just get that one term. But that is the residue, right? By definition, that's the residue of f of z at z naught. So there you go, that's the rule 1. Rule 2 is perhaps a little bit more interesting. Again, let us suppose that f of z is like that, then what is z minus z naught squared times f of z? I should be clear here. What does it mean to have a double pole? Right, so that means that, so the difference between the simple, this was, where I used that this was a simple pole in the proof of 1 was in that I started the summation right here. This is using simple. Using simple pole, right? Big N, as I talked about in previous lectures, is equal to 1. Now big N is equal to 2. In other words, N starts at minus 2. That makes it a pole, a double pole. All right, it's got only up to reciprocal squared powers. So I'm multiplying that by that. What happens? You get, it's pretty much the same calculation. Yeah, okay, well anyway, here it's similar to the rule 1, but it is a little bit different, I suppose. Here's n plus 2, right? You notice that multiplying by z minus z naught, it clears out the reciprocal powers here, multiplying by the square. Like in the previous one, multiplying by the first power cleared out the reciprocal powers, right? Because the simple pole just has like a 1 over z minus z naught. Multiplying it by z minus z naught clears out the reciprocal powers, actually. This does the same. Multiplying by z minus z naught squared clears out the reciprocal powers. It leaves you with something which is analytic. And then what's rule 2 says? It says differentiate it, and then take the limit. So what happens when we differentiate this? I'm going to add it.
It's analytic, right? So we flip the sum.
Yeah, so we can bring the derivative inside the sum, differentiate term by term, and what we got is the sum, I'll write it sum n equals minus 2 to infinity of n plus 2 times a sub n z minus z naught to the n plus 1, right?
Should we get a z or a z naught popping out somewhere?
Nope, because the derivative of z minus z naught is just 1. So now take the limit, and then, you know, as z goes to z naught, we find, you know, let me call this thing Pac-Man. We find Pac-Man just tends to n plus 2 times a sub n z minus z naught to the n plus 1 with, well, let me not write it that way.
Is it 0 or
Sorry.
n equals minus 2?
Yeah, so so yeah, this one we have what? We have, you're fine. N greater than or equal to minus 2, right? So n plus 2 is greater than or equal to 0. And so this power, excuse me, n plus 1, n plus 1 is greater than or equal to what?
Minus 2?
N plus 1 is greater than or equal to minus 1, I guess. Right? Which just seems problematic until you notice that n equals to minus 2. What could we do there? We could rewrite the summation, right? Do we need n equals minus 2 in this sum?
No.
Because that gives, yeah, exactly, that's 0. So we can just erase that minus 2 and make it a minus 1. Okay, so then n is greater than or equal to minus 1, which means n plus 1 is greater than or equal to 0, right? And then if you think about this, that just goes to 0, right? This goes to 0 for n plus 1 greater than 0. And so that whole summation just drops to the n equals to minus 1 case. Well, what is that? Minus 1 plus 2, right? Times a minus 1. Hey, well, that's a minus 1. Which is, by the way, the residue of f of z at z naught, yeah? So, do you see that this is really just the first of a whole family of such rules? If you had a pole of order n, what could you do? If you had a pole of order n, big N, you could just multiply it by z minus z naught to the n power, and then what would you do? You just have to differentiate it, not once, not twice, but n minus 1-fold times, and then that would give you the residue, except that's not quite true because then you would get burdened with the powers of the derivative. The derivative, you get like a factorial you have to address because the successive differentiation brings down powers. That's not present, that's not apparent yet because there's like a 1 factorial from differentiating once, and there's like a 0 factorial from differentiating 0 times. So we didn't see that combinatorial factor yet appearing, but
So
if
z minus, so to the third power, you get the second differentiation, which would be like n plus 1 plus n plus 2.
yeah,
I see what you're going at now.
you get an n plus 2, you get like an n plus,
1, n plus,
I guess the next thing you get would be n plus 3 times n plus 2.
and then you get the same point.
And then when you plug in minus 1, you get a 2 times 1, which would then give you, you'd end up with like a 2 factorial times a sub minus 1 if you were dealing with a pole of order 3. So there's a version of this rule for higher poles, which I haven't written in my notes because I didn't think it was interesting. I don't know why I'm dragging myself into talking about it now in class. My apologies. That's rule 2. Rule 3, how would we do that?
Oh, well, we only have to worry about the zeros in G, right?
Hmm.
And so you essentially just use rule 1.
Maybe. As a simple, let's see here. F is analytic. Well, I think I can erase this. We already agreed rule 4 follows rule 3, right? So how do you prove rule 3? It's a little bit involved and we're out of time, so I will have to relegate it to the grab bag of all proofs I didn't cover, namely the video. So, anyway, next class, what we'll do is we'll calculate many more residues, okay? And what we're going to see is that, so the residue theorem gives us a way to integrate many complex functions, right, over a closed curve. As long as they have isolated singularities, you can deal with them, right? So meromorphic functions are the natural candidates to work with this residue theorem, right? Because they've got only isolated singularities, each of which is a pole. I seem to be saying there's something wrong with essential singularities, but I don't actually have a counterexample on hand right away. I need to think more about, is there a problem with essential singularities in this theorem, in this theory? So let me ponder that for future classes. But anyway, so next up, more residue calculus.